How's it going, everyone? Welcome. I'm Leonardo Gonzalez here. And today, let's go to now finally look at this particular book that talk about how do we get here with JavaScript. So the idea of this series of videos is to understand now first what is JavaScript, how JavaScript emerged, and some of the nuance that JavaScript is, and explore about this introduction. Is this about or the history of JavaScript, and also is a particular topic that when you need to know to write JavaScript application, which is not only about a little bit of history, which is something that is important. Perhaps you might not see that if you are learning this at the beginning, but the point of this is it is important to understand how do we get here, and once we're able to understand that, now you will be at peace with yourself. You will be now somebody that can now effectively solve real life problems and translate into code to now provide solutions to business. You may wonder, why do I want to provide solutions to business? Well, because at the end of the day, they are the one who gonna pay for you skills and your knowledge. So if you want to live now a very decent life, or in other words, a life that allow you to now have better problems, okay, so instead of worrying about what am I gonna eat, or how am I gonna eat, and when do I want to eat, or when do I going to sleep, so on and so forth, you're starting to now have more time to explore areas that are more relevant as a human. So, but in any case, here we are, and this is was to elaborate this particular topic, right? So we write down about how do we get here in terms to understand the book, the name of the book, and now the history, legal aspect, the technical, as well as how that it's to now we create the entire story that makes all of those things, so that makes all of those pieces fit together, right? So this is now this particular video. So what would what's with that name, right? So JavaScript was a marketing was a plot, all right, because that was marketing. It was a plot. It was a marketing ploy to position the language as palatable. But what I really love about this particular word that they use here, because JavaScript, the name in itself is an artifact of a marketing shenanigans, all right. So because this language was designed internally by Brendan H, a software engineer back then, that worked at Netscape, the first commercial browser, and they internally know this language as Mocha, all right. Despite the Netscape or the code name that Brendan H provided to the language was Mocha, that makes a lot of sense why you are hearing like testing library called Mocha, right? And the name the name of the language internally in Netscape was the live script, okay. So because marketing team wants to now position this product to make it palatable for a Java audience as a lightweight alternative of the heavy and well-known language, right? This is now uh, they make a couple assumptions by the language, by Brendan H, that whether it's your Java or a JavaScript, you must know is the C syntax, for example, the block and how some of those things works. So because the language uh, uh, now have this similarity, but that's when the similarity ends. Okay, so the language, or in this case, the legal aspect of the language, is now something that is the trademark is now owned by Oracle through a change of acquisition. So Netscape, which was acquired by AOL in 1998, and then now AOL was a company that was acquired by Sun Microsystem, and how that company, after the bubble, the house crash, the house mark the after the Jesus, my God, after the the bubble crisis, the housing crisis in 2008. So in 2009, that company was bought by Oracle, and now the European Commission actually know that they raise some flag about some monopolistic uh, practice, and there was discovered because there was an alternative in the market now as Postgres, uh, that is now very competent at what it's doing. So, but in any case, the thing is that now Oracle owns the JavaScript trademark, but this hasn't been enforced. And quite frankly, it is quite hard that that happened right now. So the also is now the technical aspect, the technical team that actually is looking for the ways to improve the language. This is known as the technical, or the TC 39, that is responsible for updating the technical specification of the language, known as ECMAScript. So regardless how you call it, ECMAScript, JavaScript, GS, or ES to 2019 or 2020, all of this are under the umbrella of JavaScript. So please don't call this like ES8 or ES10. It just generate a lot of confusion. So it's preferred in those cases use now the ES and the name of the technical specification, which is something that recently that's what they have done. All right. So far so good. Because now, all right. Once we look at what this TC39 commit actually do to the language, which is this language specification, is a group of the it's a group of people that works in a wide variety of web-related industry, such as browser makers or device makers, for example, like Samsung, among others, and they might receive some kind of compensation for those companies to be part of the team, and also they are responsible for when the event will be hosted. This is something that is open. Everybody can participate in the discussion, all right? But only those proposals or champions that reach to the meeting, which lasts for about 3 days, are the only proposals that are valid too. So these proposals or champions that go from serious stage until approval, because we are programmers, they go from 0 to 4, right? And if a proposal or a champion make it its way up all to the stage 4, this process can take now several weeks or even years to accomplish. So that's a lot, and because there was an issue that happened with since the TC39 needs to since the TC39 needs to, at the end of the day, is to say, hey, browsers or any JavaScript implementator out there, we want you to stick to the law as much as possible. And because most of the times all of those JavaScript engines actually follow that, but some of the time they don't reflect the current state or the reality of the web. And because of that, there are now, for example, two cases that are quite interesting. One of them is the method includes, which before that, the initial proposal is call that method contains, but because there is already a particular library that use that in some small subset of websites out there, so they decide to rename that to call them include. That's one. And another, which is more interesting if you want to dive deep into this, known as Mushgate, all right, where again this is 39 wants to now implement a feature on arrays when they wants to flat the dimension of an array, and they want to call it is flattening, right? So because of that, and there already were a library that in Deutschland use that name, and not only that, because you can replace that or override that behaviors, but the problem is that that library also were manipulating its DOM and doing some other kind of DOM operation. So doing so, it will break the web, and it was a tragic and comic situation that happened. The thing here is that they have to rename that to flat, all right? But again, despite of all of these cases that happen, most of the time those JavaScript engines now stick to the law, and those who doesn't, because again, perhaps the TC39 is not well aware of the current state of or the reality of the web. They're now in a particular appendix in the spec that now describe in details what are these specific behaviors that some JavaScript or that JavaScript can have or produce. So this particular mismatch that can happen here, right? And so these are well documented known behaviors, all right? Again, due to the nature of the reality of the web, and because of this mismatch, which is when it comes to now describe or look at the entire collections of environments that you can run now JavaScript, whether it is the web or the browser, the server, the light bulb or robots, you name it, right? So one of the things that a lot of developers, the mindset is mismatching or is creating some of these bugs or complaints about it, is that when they go a particularly environment, they run code that they think they have certain particularly tools. So, for example, like alert, or fetch, or get current location, or get media. Well, which is get media. Let me see if I can find that. Yeah, or get user media. All right. And all of those now live is on the browser. And when it comes to the server with Node, we can now write or read files synchronously or asynchronously, right? So the idea of this is this mismatch that can happen, but again, it's on the JavaScript developer mindset. It's depend on the environment in which you are running the code. So because all this huge variety of environments that we have, right? And hopefully I think that that's just going to increase. Okay, so all of these environments, right? Now, yeah, all of these environments that we have, uh, if we want to know, for example, and a good question is that, so if we have all of these particular environments, uh, how do we know which specifications actually is the source of truth? All right. So this is when now the web, despite all of these environments, all of those JavaScript engines must stick to the law. The web practically is the reality of this implementation. So even though that you look at this implementation, all right, and despite that you have, for example, is some convenient tools, for example, in the browser environment, all right, or the server, but specifically on the environment here in the server, on the developer tools, when we think incorrectly that this actually is now a true JavaScript environment where it's going to behave the way it needs to be done, the assumption is wrong. Why? Because those environments, especially here, you can they don't behave according to the ECMAScript specification. One example of that is when you type use a string, when you press uh, uh, enter, or when you hit enter, the entire the entire console season is going to be on that mode, which is something that is not the truth. So user string is gonna be on it on if you put that at the top of the file, it's gonna behave like if you put at the top of the file. But again, it only works is at the file level. But again, since we are here in this environment, as a way to now things more friendly to JavaScript, this is one of the nuances. The other is that when you create now a function or a variable, it automatically attaches those to the global object or to the window object, where the reality does not. Okay, on a JavaScript function, on a JavaScript environment, that's not how that works. So that is a good example. That is a good example that I want to dive deep. Okay, I definitely want to dive deep into that example by saying, hey, I want to get into the node, right? And once I am here, I want to say, hey, if I define this, all right. If I define, for example, a var called var1 with a value of 1, or if I define now a function here called function1, all right, that is gonna console.log is say, hey, this is now console.log here, all right, and say, hey, function one, all right. So if I want to inspect that in the window doesn't exist in this particular environment. So what happened here? Exactly. The thing here is that now those particular environment has a particular way to handle those use cases, right? So this, especially this example is something that works on browsers, but not on the environment, all right, or in server, where it attaches it to the global object or to the global this. You call the global this, right? But there is no reference there. Or to the global this, right? So again, that particular behavior is explicitly to the browsers or to the server, and they're gonna behave different. This is why it's important to, especially if you're going to uh, test your small functionality in the developer tools, especially in the JavaScript console. They are good. They are a friendly JavaScript environment, but they are not JavaScript in itself. All right. So not only that is that because we in here we can write our code to describe certain functionality as a way to test that on our developer tools, whether it's on the browser or the server, all right. But when it comes to now write long applications, right, thousands of lines of code, right, to tell how this application should behave and what it's supposed to do, yada 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 yada. They are now different style of programming to describe is this particular stuff, which is how do you describe a problem and a solution. Okay, so we have now procedures, which is the way of how you can now is organize your code from top to bottom, all right, in a linear progression through a series of determined series of operations. Hey, we need to do this and then do this and then do that and then do that, right? And all of these units are called now procedures, all right? Or you can use now a class oriented or object oriented, which say, hey, let's go to now describe the data and the functionality, the data and its logic into one single unit called class or called class. And this is a good way of how you can now communicate different nodes or different classes here. And the other is now the functional approach, which say, hey, let's go to now is create pure function that allows to run as this pure computation, doesn't modify the state of the application. And if you want a new desired state, you're just going to recreate a new function. If you want a derivative state, okay, and the adaptation of those functions as variables. So the idea of this different approach is that we can now have at least is one particular or multiple particular way to describe to is to is to uh, is to describe a problem, all right, which are orientations is that, hey, how should we approach to a problem and solutions, right? Is this linear way of doing this kind of stuff, or it can be now encapsulating is the data and it is logic, so we can now communicate with another ones, with another models, all right, and then exchange that data, or is by just describing it as a function, pure function, a function that doesn't modify the state of the application outside of that. And if you want new the exactly, and if you want to now a derivative state, you're going to create now a new function uh, for that, right? And store that into a variable. So all of this is just to look at the different style that we have here in JavaScript, which is the multiple paradigm language that we can have, all right? And a very important topic, especially that when you need to provide is the support for your applications, which is, hey, now that I write all of this code, how can I guarantee that this code will work in the next 5 and 10, 20 years? Is this sustainable? All right, this is known as the backward and forward compatibility. So backward compatibility is guarantee essentially that we rely on tools that allow us to do or this backward compatibility means uh, is that older JavaScript can be executed by the current JavaScript engines, all right? Unlike CSS and HTML, that they are forward compatible, all right? And they're the scripted language, right? So perhaps some of the code that is being used in 2000 may not work properly in 2025, right? So the idea here is that with this compatibility, okay, we have now tools that allow us is to guarantee is this backward compatibility. So for example, like Babel, okay. So when you want to now provide specific behaviors to that, and a particular behavior is, for example, in the case of finally. So finally is a method from the promise that is in 2019. That method was implemented, but previous code, of course, doesn't have that. So we need to find a way to actually simulate that behavior, and this schemes or way to now describe how you can is feel that. Mm-hmm. It's always an illustration. Official polyfill. So here they're describing is the shims, okay? So and to guarantee now forward compatibility, let's say an API or method that is not available in current browser, they still. This pattern is called like shim. Okay, so this is where things stop a little bit. Exactly, filling the gap with polyfill, and now jumping the gap mm-hmm. Mm-hmm. So the polyfill or aka shim is just a way to now provide is forward compatibility. Mm-hmm. This pattern is called a polyfill, aka shim. Okay. So if you want to now provide is backward compatibility, as well as forward compatibility. All right, we use now is those polyfill or shims in our code that allow us to use is the new JavaScript syntax, and then through a build tool, usually Babel or any other tool out there, TypeScript, you name it, uh, you can now is to deploy that in a particular browser that understand that. So you can now is through Babel parse that into a JavaScript code that that particular browser can understand. There is also a table that allow us to now look at the support of specific features of that. And I think that's very good segue here because we can actually see that the web status is a very interesting website that we can take a look at this. All right, at least from the baseline 2020. Uh, just to describe is this huge summary of how can we do this and so on and so forth. So I really love about this because that's something that is very interesting to look, and you can actually see is that in real time how certain features are supported and some others not, and what is the recommended approach to use each one of them. So because this process of uh, guarantee this backward compatibility, whether it's when our code is running, so in other words, when our code is running, which is our code is so is the browser can execute current up to date code, evergreen code, or do we need to rely on some particularly transpiler or Babel? And the name transpiler is just a fancy way to say, hey, this is now a process that transform is from one language to another language, high level language to another language. Unlike compilation, which is transforming is that from a high level language to now a machine readable code. So we mentioned this is because when it comes to now understand how the language is compiling or interpreting the code, the answer now relies on the detail because programs at the end of the day they are now a set of instructions, or traditionally, okay, programs are now a set of instructions that sits on disk ready to be executed when the OS or you that interact with the OS calls them, which is in reserved space in memory, RAM, all right, and then now it's going to load that set of instructions there. So now the CPU can process that, and aka creating now a process. So a process is something that perhaps let me just refresh here for those who are not quite familiar with. So a process now is this program that is being executed by the CPU and now run on the main memory, and it has now a well-defined section in memory. So one misbehaving process cannot influence or interrupt or broke others, all right, which is one of the interesting quality. So for example, browsers like Chrome famously are known to anytime that you create now a tab, all right, behind the scenes what it's doing is to say, hey, let me now is create a process for, and there are now several examples of those processes, such as program counter or program stack trace, or the register processors, all right, it is fairly to say that each of one of those examples or processes actually live inside of a thread. And a thread is a single unit of execution that that is defined, and I would like to actually talk about here to this. So a thread that is a single unit of execution, okay, it is safe to say that is defined by the OS. Yes, that's correct. A thread is a single unit of execution, is indeed defined and managed by the operating system. And because they are the ones who decide what is a unit of execution, or unit, exactly, a unit of execution, you can think of this unit of execution like what is the single, the what is the unit, okay, of time, distance, weight, all right? So you have kilogram, you have meters, you have seconds. And I say kilogram because I live my entire life with the metric system. And for those who live in the jars, that kind of systems, to me is like, I wish you the luck. I wish that at the end of the day, they're just units, bro. They're just units. But this is important to understand. Anytime that you read about unit, all right, ask yourself, who defined that? Who defined a unit, bro? And in this case, this unit is defined by the OS, which is now creating and destroying threads, all right? So this is something that is going to be passed down to the processor, all right? So how now the OS actually pass or switch on and off these processes and threads, right? It does that through the scheduler. So the scheduler that lives inside of the OS is responsible to take now the thread or processes, all right? In the case of the processes, it's gonna require now to save the state of the program and all of the threads, as well as all the other data around that, and manage as well the virtual memory that needs to be allocated or deallocated, all right, to switch in or off a process from to a processor, all right. And because now, since processes have this unit of execution, these threads that live inside of them, they now able to share its memory or the heap, which makes them a little bit much more performance when it comes to switch between threads. This is known as the threads switching or processes or context switching, because this context switching that can happen in processes and threads, okay? So context switching is something that happen in processes and threads. Exactly. So you have this process context switching and thread context switching, and since this thread context switching is way much less expensive than processes context switching, especially because it doesn't have to add more space in memory, or managing is the space on that, there are now some alternative to that particular approach, which is known as a coroutines and yeah, which is known as coroutine. All right, which is known as coroutine. And the other is a particular process that is known as coroutine. All right, and the other is something that React is actually using behind the scenes. They're starting to use that behind the scenes. Fibers. All right. So these particular processes are now delegating is the uh, concurrency at the application level that periodically needs to yield control and gain impact when executing is a processes or when executing is a program. So again, I mentioned that and I described that. It's just to fill the gap that between this or traditional now how programs has been executed, okay, that the way of how these programs are generated is based on this uh, compiler or interpreter, all right? So traditionally, the history of programming language has looked with disdain at this interpreted language because they are not uh, optimal as a compiler. And the reason is because instead of you already have the entire program already translated into machine code, aka into a portable version of the executable code that works on that particular architecture, all right, whether it's on Windows or an Android, Window or yeah Android, like APK or EPA, or in the case of iOS, or the EPA or the app, or the window like the executable, all right, or the MSX, which is the like the wizard, all right, like the onboarding installation, okay, uh, or the different executable binaries across the entire collections of a yeah across the entire collections of Jesus distros, all right, whether it's the DOREM or the RPM or you name it, right? So those compilers, all right, or interpreters. Uh, so this is when now, and this is one. Uh, this is one thing that the history of computer and also the programmers actually disdain this kind of interpreted language because they're not optimized, and the other is that uh, they are not they're not mature, uh, like for example static languages where they already tell you is what is the type of this particular variable and so on and so forth. Nevertheless, all right, because those language, regardless that are compiled or interpreted in this compiled version, they are now produces this portable binary representation of the program that is distributed for execution later in that architecture. All right. So, because JavaScript, when you really dive deep into the engine, it doesn't work that way because we distribute is the source code, not the binary form. All right. So many claim that that's disqualified JavaScript from the category. But the reality, the distribution model for a program executable form, okay, or the execute the this is interesting. The distribution model of a program executable form has changed dramatically, uh, or has become drastically more varied and less relevant in the last decade. So the question at heart is doesn't really too much about that, but it lies way much more is on how now the language handles error. Is the nature of this, because the real thing that really matters from all of this explanation, especially with the interpretation, and I really love that I have to step in here to recognize that, to decide here, to look at this, to be able to describe this, is because of that. It's because we went through the scribe now here, especially that uh, if you want to provide now backward compatibility or forward compatibility, uh, whether if you're using a particular transpiler to do that, to guarantee always allow you to write is the evergreen JavaScript code, regardless the if those browser vendors or environments actually support that, okay? And you can make use of the new JavaScript features and make it air their benefits as well as trade-off, all right? So this particularly compatibility, or the backward compatibility or forward compatibility, or this code that needs to be right, okay? They need, we need to know what is this code looks like, or we need to know is who compiles or interpreted that language. What is the process of executing that language? All right. What is the process of execution? So because of so this process of execution, okay, which now traditionally programs, compile programs, is now that they are going to generate is a binary representation of the machine code of those instructions in a portable way that can be distributed and execute later in that architecture. That's great. So this is one of the things that the history of programming has disdained all of this a interpreted language, because they are not that optimized, they're not that performance as compile, because you already have the entire instructions there generated, all right? Whereas the also they are not more mature like this type, uh, so they're not too mature of this type, or the static type programs. Again, JavaScript, it has now, or this interpreted language allow you to define is a prototype much more quickly. Is that what you want? And especially in the era of all of these startups that they are trying to find their way to become a monopoly, sort of speaking, okay? But the thing here is that JavaScript doesn't behave like that way, because JavaScript is a source code, but it is not machine code, all right? Exactly. And because of this, a lot of people actually disclaim or disqualify, exactly. A lot of people disqualify that the JavaScript is a compiled language, right? But the thing is that because this discussion is something that is broad, and now the term in itself has changed dramatically and evolved with the years, with the decades. I think the question that is much more relevant here is to say why JavaScript is throwing errors. And when that happens, when JavaScript throw errors, and how JavaScript actually throw errors. So if you're an interpreted language, how do you know that there is an error that happened? Okay. Or how you do detect, how do you determine when an error happened? So the thing here is that most people think that this is scripted or interpreted language were executed in general from top to down, right? One line after the another. But the reality here is that in a scripted or interpreted language, an error on line 5 won't be discovered until it reaches to the line until lines 1 through 4 have already executed, right? And notably, the error on line 5 might be due a runtime condition. So such as some variables and variables that are unsuitable value for operations, or it may be due to a malformed statement command on the line. Depending on the context, deferring error handling to the line the error occurs on maybe a desirable or undesirable effect. Compare that to language which do go through a processing step. Typically, exactly. So this is now describing is that how now language detects error. So for scripted or interpreted language, if you have, for example, now an error in line 5, okay, it has to go through line 1 to 4 to detect that error, okay? Notably, the error on line 5 might be due to a runtime condition, such as some variable or value having an unsuitable value for an operation, or it may be due to a malformed statement command. Depending on the context, deferring errors handling to the line the error occur, or maybe a desirable or undesirable effect. So if you compare now with the compile language, okay, like this. So compare that to language which do go through a processing step, typically called parsing. Exactly, before any execution occurs. An illustration is like this. So if you compare now to a compile language, it goes through a process of parsing, which is going to evaluate all of the different strings, or it's going to evaluate all of the characters in a different string, and then recreate and build now a digital representation of this program, aka an abstract syntax tree. All right. So now the computer understand how is the instruction needs to be executed. All right. Now that he have this internal representation of this now as the abstract syntax tree, this is why it's important to look at data structures and so on and so forth. You know, you name it, yada 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 yada. So despite of that, okay, what do we parse language have in common with compile language? First, all compile language are parsed. So a parse language is called a weights down the road towards being compiled already. In classical compilation theory, the last remaining step after parsing is code generation. The last remaining step after parsing is code generation, producing an executable form. Okay, the last part in compiler theory. Okay, so in compiler theory, the last step after parsing is code generation. Interesting. Interesting. In compiler theory, the last remaining step after parsing is code generation. Is this executable form? All right. Is this portable executable form that can be distributed to be executed later on in that particular architecture? once any source program has been fully parsed, okay, it is very common that its subsequent execution will, in some form or fashion, include a translation from the program form of from the parse form of the program, usually called abstract syntax tree, to an executable form. So what it's doing here is this compilation, these programs here, okay, these compiled programs that is going to evaluate all of the different tokens, and then is now create this digital representations that the computer can handle it, all right, not execute it, that it can understand is the structure of this, okay, because this is what it's doing. Once a source program has been fully parsed, it is very common that its subsequent execution will, in some form, include a translation from the parse form of the program, usually a call abstract syntax tree, to that executable form. Okay, so the process of parsing is transform that into an abstract syntax tree. Okay, which this abstract syntax tree is this digital representations of is the digital structure representation of your code, all right, which is how do you know that you are here, sit down, or you are in front of a computer? Well, because you at least know some stuff about this, that you are in front of a computer, that you are sit or perhaps walking or dancing. I don't think dancing, but still walking or stand up or listen to me right now at some point. Might be cooking, or perhaps you live this in the future, just transmit it over your brain directly, so you're now downloading that. Holy moly. All right, but this is the process here. So it's going to transform now this parse. It's going to transform this parse, or it's going to convert is this code compilers. We're gonna do that. It's gonna transform the entire code, all right, the entire document here, the entire code. There can be several pages of that into now a abstract syntax tree, which is this internal structure that the computer has to understand that it can now transform that into an executable form, which is the binary code, all right, or an executable form, all right, a program. So once any source program has been fully parsed, it is very common that it's exactly. In other words, parse language usually also perform code generation. Parse language also usually involve code generation before execution. So it is not that much of a stretch to say that in spirit they are compiled language. All right. So any parse language also usually also perform this code generation. So in the spirit they are compiled. But the point of this is that look at the similarities between a parsing process that usually involves is code generation, all right, that the compiled languages generate is now this executable binary representations that is portable, ready to be executed at some point, that can be distributed as long as it is in that machine or that architecture. Okay, so the similarity here is that parsing here is that parse usually involved is to generate that code generation. That's when it comes here to the compiler theory here. So because in parsing, an interpretation is like that, all right? JavaScript source code is parsed before it is executed. The specifications require as much because it calls for early errors. Mm-hmm. So the JavaScript source code is parsed before executed. And this is the distinction here. The JavaScript source code is parsed before it is executed. The specification require as much because it calls for early errors. Statically determine errors in code, such a duplicate parameter name, to be reported before the code starts executing. Those errors cannot be recognized without the code having been parsed. And this is quite interesting. Very, very, very interesting. So JavaScript is a parsed language, but it's compiled. The answer is closer to yes than no. So JavaScript is a parsed language. Okay, the source code is parsed before it's executed. And when you talk about this parsing, is that it's going to transform that script into an abstract syntax tree, or this digital structure of your code that your computer can now produce. Is this usually a executable form? But JavaScript is parsed before executed, which means that it can early detect errors, and this is when the confusion comes here with a lot of people here. So JavaScript is a parsed language, but it is compiled. So the answer is closer to yes. So than no. The JavaScript parser is the parsed JavaScript. All right, is optimized. Is converted to an optimized binary. Interesting. So the parsing, all right. So the parsed JavaScript is converted into an optimized binary representation called as bytecode, all right, or a binary representation, and is subsequently executed. So it's going. So the parsed JavaScript is now subsequently executed here. So the engine does not commonly switch back into line of execution, like in figure 1 mode, after it has finished all the hard work of parsing. And most language engines wouldn't, because they will be highly inefficient. So to be specific, this compilation produced a binary bytecode code. This parsing produced a binary bytecode, or sort of, which is then handed to the JavaScript virtual machine. Holy fuck. So first the code is parser, okay, and this parse is now converted into a binary representation, into sort of binary representation, okay, which is is an intermediate step, the bytecode, that is passed to the JavaScript virtual machine to execute it. Okay. To the JavaScript virtual machine to execute it. Some like to say this virtual machine is interpreting the bytecode. But then that means Java and those other JavaScript driven language for that matter are interpreted rather than compiled here. Of course, that contradicts the typical assertion that Java are compiled language. Interesting, while Java and JavaScript are very different language, the question of interpreter and compile is pretty close related between them. Another wrinkle is that JavaScript engine can employ multiple passes of just-in-time processing optimization on the generated code. That's another one. So these engines can pass or can do some multiple passes of just-in-time processing optimizations, which again could reasonably be labeled either compilation or interpretation. Depending on perspective, it is actually a fascinating complex situation under the hood of a JavaScript engine. So, what to do these nitty-gritty details boils down to. Step back and consider the engine flow of a JavaScript source program. First, after a program leaves the developer editors, it gets transpiled by Babel or for any other transpiler, okay, and then packed by Webpack or any other model bundlers, all right, and perhaps half of those in other build process, all right. So by the time that code leaves my code editor, it's going to be transpiled to something that can be understood, and then bundle up by a model bundler, all right, or processed by other build processes, and then it gets delivered very different. Then it gets delivered in that very different form to a JavaScript engine. So that JavaScript engine takes that script, parse it to convert it to an abstract syntax tree. In this case, it can be the client here, and then the engine convert that abstract syntax tree to a kind of bytecode. And then the engine convert that abstract syntax tree into a kind of bytecode, a binary representation or this intermediary representation, which is refined and convert even further by the optimizing just-in-time compiler. All right. So the engine convert the abstract syntax tree in this intermediary binary representation, okay, which is now our refine and convert even further by the JavaScript optimized compilers. All right. So that binary representation or that intermediary binary representation is now even further than is that even further refine and convert by the optimizing just-in-time compiler. All right, and finally, the JavaScript virtual machines take the program and execute it. So to visualize those steps, again, will be something like this. It generates the entire JavaScript. Okay, so by the time that your code leaves the code editor, all right, it's gonna be transpiled by any transpiler or by Babel, and then that code transpile or even with TypeScript as well, all right, transpile. It's gonna be transpiled into that code, all right, bundle up and deliver it in that form to the JavaScript engine, which can be your server, it can be the browser, light bulb, a robot, you name it, right? So that JavaScript engine parse that script, okay, and convert it into an abstract syntax tree. That abstract syntax tree, the engine convert into some binary intermediary representation, bytecode, depend of the JavaScript implementation of that. All right, that, and then this intermediary representation is even further refined or converted by the just-in-time compiler engine. All right. And once that is done, now the code is finally executed by the virtual machine. Holy moly. So, figure 3, parsing, compiling, and executing JavaScript code. It is JavaScript handled more like an interpreted. So, is JavaScript handled more like an interpreted line by line as figure 1, or it is handled more like a compiled language that is processed in one several pass it first before executing and in figure 2 or 3. Exactly. I think it is clear that in the spirit, it is a compile language. If not in practice, it is a compile language. But it's because of that. Again, the reason that matter here is that JavaScript is a compile language. JavaScript is a parse language. But it's because of this question: how JavaScript handles errors. You know, how JavaScript handles errors. And again, the reason that matters is since JavaScript is compiled, we are informed static errors such as malformed syntax before our code is executed. And this is a substantially different interaction model than we get with traditional scripting programs, and arguably more helpful, but especially for malformed syntaxes. For malformed syntaxes to detect this early message. So, for example, if you say something like this, var var1, or I can say is fruit 1. Say apple, right? You say var fruit 2. You say bananas. You say a function here that is fruits, or printFruit, right? And you got is this, which is well, console.log of fruit 1 and fruit 2, right? And then here you say, hey, I want to now console.log printFruit, all right? The console.log that, and here do some mistake here. Say console log, right? So what happened here is that because I defined this error here, it shouldn't even evaluate all of this, right? It should give me is a syntax error. But the thing here is that it's now evaluating this. This is now a reference error, not a syntax error. All right. So if you, for example, now reload this and say, well, how do you generate a syntax error? What I'm gonna see is that's a good question. Syntax error. So for example is va gonna say variable, no, because we're gonna throw is a reference error, syntax error, how to produce syntax error. Let's just say is syntax error. So how to generate a syntax error in JavaScript? Okay. Okay, okay. Invalid variable names. Oh, invalid. That's a very. Uh, one fruit. Okay. Three fruit, which is mango, right? And it's like this. Early detection errors, bro. Early detection errors. Early detection errors here. Early detection errors here. Absolutely. Early detection errors here. Early detection error here. Mm-hmm. Interesting. So with var is one of those errors. Malformed string is another one. So we can say it's this. Fruit 3, and then do something like this. And then it catch you the syntax error. So in other words, that JavaScript is a compiled language, aka a parsing language, because it's actually, before evaluating all of that, is parsing that language for early detection. All right, and I think this is quite interesting. And I think this is a very interesting exercise. So JavaScript is a parse is a parse language to prevent or to detect early errors, right? JavaScript is a parse language for early detection, for for early detection errors. Exactly. For example, what is what is the result of this code? That makes a lot of sense, bro. Absolutely. For early detection errors. So for early detection errors, man. Holy moly, bro. Exactly, for early detection errors, man. For early detection errors, man. Hmm. That is very, 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 very interesting. So this is a bit helpful. So this is a bit helpful than just any program, so that just any interpreter where it needs to run the code come the code up up to that error up to that error. So this early early detection errors are helpful. Holy moly, bro. God damn. Holy moly. Strictly speaking. Holy moly. Holy moly. Holy moly. So that'll be all for this video. Take care. Bye bye.